Hi y'all, this is our lecture 1 summary for week 12, and this lecture was looking at logistic regression. And the first kind of, bit of the lecture was reviewing 2x2 tables. The reason because is we've talked about odds ratios already, and that is a major concept associated with logistic regression. So just as a review of those, I think we covered these in week 7, I want to say it was, but focusing specifically on the odds. So in this case, we're looking at this example of if they received the vaccine or if they didn't, and then looking at if they had cholera or if they did not have cholera. So when we're calculating the odds, it would be the probability that the outcome occurs divided by the probability that the outcome does not occur. And the odds ratio would be 2 odds calculations over one another. And in this case, we're looking at the odds of an exposed person having the outcome compared to an unexposed person having the outcome. So in general, when we're looking at odds, if it's greater than 1, it means the group in the numerator has a greater odds of the outcome. If it's less than 1, then the group in the numerator has a smaller odds of the outcome. If it's equal to 1, both groups have equal odds of the outcome. And that's actually the null value when we're looking at odds ratios. So if we wanted to calculate with a 2x2 table, we do, there's a couple ways of thinking about the formula, but you can do A times B divided by C, or A times D divided by B times C. That ends up being, if we just do like a little bit of math here with fractions, we end up, that's what the math is showing here. So A times D divided by B times C. And we get an odds ratio of 0.25. So in this case, subjects who were vaccinated had a 0.25 times less odds of cholera compared to subjects who were not vaccinated. So that's just a review. We've covered this example before, but just a review of how we do interpretation with odds ratios and kind of generally what we're looking at with odds ratios. And we're going to extend that now into logistic regression. So we use logistic regression when our outcome now is binary. It's a yes, no, 0, 1, something disease, no disease sort of situation. So up until now, we've been dealing with outcomes with simple linear regression and multiple linear regression that are continuous. But logistic regression is used when we have a binary outcome. And we determine how different predictors affect the odds of having that outcome. Because since the outcome is binary, we can't really talk about, so much an amount increase in the outcome like we have been with simple linear regression because it can only be 0 or 1. So we're talking about the odds increase of the outcome kind of occurring. So generally, this is one way that you can think of the kind of model for logistic regression. The outcome is going to be the log odds. And then you see on the right here, this looks very similar to what we've already seen. The only difference here is what's on the left here. Instead of it just being y, the outcome is now log odds. And then each one of these beta coefficients would be telling us when x changes 1 unit, how is that affecting the log odds. So if beta 1 or beta 2 or beta p, whichever beta p, if it's a positive number, it's increasing the log odds of having the outcome. And if it's a negative number, it's the increasing x decreases the log odds of having the outcome. That's kind of generally, but as we'll see on the next slide, log odds is not a wildly useful thing to be interpreting. What does that even mean to anyone? I don't know. It's just not useful to be looking at in that framework. So instead, what we do is when we have that log of a value, we can back transform that. I refer to it as just exping it. So you do e, which is a constant within math, but e to the power of each one of those beta coefficients to get rid of that log component. And Stata actually does this automatically for us. So that part you don't have to worry about doing yourself. That's kind of what's happening behind the scenes. But then instead of getting estimates associated with the log odds, you'll just get estimates associated with the odds. So after you do that back transformation, then you can interpret stuff just in terms of how are the odds changing as the x variable changes. So in one example, or there's two examples down below how we interpret the beta coefficients. The big difference here is it's not saying as this increases this amount. It's not an additive change anymore. That's what we saw in simple and multiple linear regression. So we saw if age increases 5, blood pressure will increase X amount. But here it's saying now it's multiplicative. So in this case, for every year increase in age, the odds of the outcome are 1.05 times greater. That's where that multiplicative part of it comes in. And you could also convert that to a percent. You do 1 minus that odds ratio, and you get the percent. We've talked about that previously as well. You could say the odds of CHD increase by 5% for every 1 year increase in age. So it's a 5% increase is still a multiplicative change. It's not an additive change, because 5% will vary based on what the actual change is. All right, and then there's also one for if we had a binary variable. So in this case, it was looking at smoking. So people have smoked in their life. If we got an odds ratio of 2.34, it would mean that people who smoke in their life have 2.34 times greater odds, or you can convert that to a percentage, to 134% higher odds of having CHD compared to people who have never smoked. So still kind of generally what we're looking for is doing an interpretation. We want to look at the confidence interval. We want to look at the p-value. I don't talk about that here, but there's a lot of parallels between linear regression and logistic regression with how we kind of want to talk about and summarize our results. The difference here is just what are these actual coefficients that we're getting estimates for in Stata. There are some assumptions with logistic regression. So one of them is that there is a linear relationship between the log odds in each predictor. The other assumption being that the no interactions between the predictors beyond what's already included in the model. We still have that independence assumption, so the subjects are independent from one another, and that we don't have any multi-collinearity. So it's a little bit more simple here with logistic regression. We don't worry as much about the assumptions generally, just because they're a bit more straightforward. And just as a note with logistic regression, if we want to compare models, we can use AIC or BIC. Smaller AIC means that it would be a better or more preferred model. All right. So again, with this lecture, this is a very brief introduction to logistic regression. Again, it's one of these topics people spend a lot of time on, so I'm not expecting you to be experts on logistic regression, just kind of learning some of the basics, especially kind of the basics of doing some of the interpretation. So I wanted to look at just going through the homework tips document, so using that data set, and just kind of walking through how do I do a logistic regression within Stata. So I'm going to exit out of our PowerPoint. Then open this up, and I already have that data set in here, so if we look at that data set, we see the outcome that we're interested in is admittance. So it was looking at, did someone get admitted into college? And I don't know, this must be grad school because of the GRE. I'm not totally sure. No, that can't be. Is that the GRE? That's not what GRE scores. Well, I don't mean it says it's the GRE. I'm trying to just remember this data specifically. Maybe that is what GRE scores are. I don't know. It's been a while. Anyways, it's looking at admittance. Because of the GRE, I think it's grad school admittance. And it's looking at, was that person admitted, what's their GRE, what's their GPA, and then rank. I'm trying to remember what that variable was. Rank a binary variable if the institution is of high prestige or 0 otherwise. All right. So this is our data. So what we were interested in is treating them being admitted as the outcome and seeing like, okay, is there some sort of relationship with what their GRE score, what their GPA is, and the rank of the institution. And those are things, you know, I kind of think, okay, if you have a higher GRE score, maybe you're more likely to get in, or if you have a higher GPA, maybe you're a lot more likely to get in. And I would think if it's a more prestigious institution, maybe you'd be less likely to get in just because they're that's them. But yes, so let's look at just running that logistic regression just so you all feel comfortable with kind of how to do that within this data, and we'll walk through the interpretation. I know this is in the homework tip sheet, but sometimes it just helps walking through together. All right, so to run logistic regression, what we're going to do is we're going to come up to statistics. We're going to go to binary outcome. So that's kind of nice, just a reminder, it is binary outcome we're dealing with. So if you have a continuous one, don't click on binary outcomes. And we're going to go to logistic regression. Our dependent variable, that is our outcome variable. In this case, it's admit. And then the independent variables are GRE, GPA. And then for rank, we're going to define what the kind of in the output, we could be comparing prestigious to not prestigious, or it could be comparing not prestigious to prestigious. It doesn't matter which one you do. The interpretation ends up like saying the same thing. It will just give you slightly different odds ratios. So we're going to come in, I just clicked on these 3 dots here to define that. We're going to come to a factor variable. We're going to, from this drop down below here, we're going to pick rank, and we're just going to pick base equals 0. So that means that I'm comparing in the outcome, it's going to be looking at the prestigious schools compared to the not prestigious schools. So, oops, got to add to var list. I always forget to do that, and click OK. So just added that rank variable there for us. Okay, so that is everything. And we can come to, if you want to, within reporting. We're not going to change anything there, but you could report the estimated coefficients instead of the odds ratios. But we don't really want to do that because that's just extra work for us to not get those results specifically. All right, so running at that logistic regression, and it just takes a minute to give us the output. Okay, so then we have the output here. This matches what we see in our homework's tip sheet, so nothing that noteworthy there. But let's go about interpreting these different variables. So GPA and GRE, those are both continuous variables. So when we're talking about those, you want to kind of think about, okay, if their GRE scores increase 1 unit, how does that affect the outcome? So in this case, if GRE increases 1 unit, the odds of acceptance increase 1.002 times. So it's pretty small. But the 1 unit increase in GRE is also not wildly kind of meaningful to look at because the GRE scores are larger. So you could look at, what if my GRE increases 10 points or 50 points? How is that affecting it? If we wanted to do that, we would do this odds ratio to the power of whatever unit increase you want to be looking at. So instead, if I wanted to look at in the homework tips, we talk about a 10-point increase. So in that case, it would be the 1.002282. Make sure you don't round it all because we're multiplying that number a lot if we're doing to the 10th. And then we'd get an odds ratio of 1.023. So that's telling us that if our GRE score increases 10 points, the odds of acceptance increase by 2.3%. And again, this is after adjusting, sorry, I didn't say that earlier, after adjusting for GPA and an institution's rank. Alrighty, so that's looking at GRE. When we're looking at GPA, this is saying if my GPA increases 1 point, my odds of acceptance increase by 2.373 times. So that's just telling us, if my GPA, and again, a 1 unit increase for GPA is quite large. That is a pretty sizable increase in the GPA, since GPAs can only really range from, I guess technically 0 to 4. But it's saying that, we see a pretty substantial increase in the odds of it being accepted. And then when we're looking at rank, this is telling us that the odds of admission for the higher rank institution is 2.56 times greater than the odds of admission for the non-high rank institutions. And I think that's kind of interesting. That wasn't exactly what I imagined. I kind of wonder so your odds of acceptance are greater for the prestigious universities. I don't know. That's just kind of like, I guess sometimes we just don't. It's not the relationship that we expect to see, and that's okay. But again, since that's comparing, that's what that little 1 dot means. It's saying that this is the odds ratio for the prestigious schools compared to the not. or the highly ranked schools compared to not. So it is kind of, when we think about this odds ratio as being a fraction, as I talked about earlier, it's looking at in the top, in the numerator would be the high ranked school, and then the denominator would be the lower ranked school. And then I have the constant there. We're not really looking at the constant too much in this case, just because the focus is on the actual variables themselves. Those are what we're most interested in when we are looking at the logistic regression output. Much like with linear regression, we are focused on these actual estimates that we get. When we look at the estimates, we get the p-values down here in this column, so we see that they're all significant. And then we also get the 95% confidence intervals. And as we'd kind of expect, because the p-values are significant, none of the confidence intervals overlap with 1. So that's just telling us that, those two things kind of match with one another. If the confidence interval contained the null value, in this case it's looking at the null value of 1, then we would expect the p-value to be greater than 0.05. So that's kind of everything for now. You'll be doing logistic regression on the homework, obviously, but hopefully this kind of just gives a nice little walkthrough of how you look at the output and kind of do some of the interpretation with it.